Hi everybody, and thank you for the invitation to this year VI-grade Summit. I am Flavio Farroni. I am vehicle dynamics researcher and applied mechanics professor at University of Naples, and I am CEO and co-founder of its spin-off company MegaRide. Today, I'm going to describe our approach to tire digital twin development in a journey from real-world data to performance optimization and real-time simulation applications. Few quick notes on who we are. We are researchers. We are a research team focused on vehicle dynamics and in particular on tire rod interaction testing, analysis and modeling. Since 2016, our research activities brought to the development of a startup and spin-off company called MegaRide, aimed to the creation of a multiphysical and modular tire simulation platform and to promote the vision of science applied to races. Few more details on our quite young company. In 2018 and 2019, we were awarded as Tire Technology of the Year and as suppliers of the Vehicle Dynamics Development Tool of the Year. Our team and revenues are growing quite fast and in increasingly growing market, trusting us and our approach to technologies, both in motorsport and in manufacturing industries. As concerns the scientific team behind MegaRide, MIT awarded us as Young Innovators Under 35 in 2018. We promote every year research programs for master and bachelor theses and PhDs, allowing us to open new and innovative channels of dialogue with automotive and motorsport players. And we are supported by a testing facility called Tire Lab and settled in our academic building where we can test and identify tire parameters for our models. Let's go deeper with our methodologies. A nice quote from Henry Mencken says that for every complex problem, there's a solution that is clear, simple, and wrong. And we think that this complexity of the tires, for whose comprehension and reproduction is needed to take into account a wide range of overlapping and competing phenomena, means to promote a holistic view in tire modeling, able to provide reliable information on all such effects. The solution to this complexity, in our vision, is the development of a modular and modeling platform. We developed two performance tools able to take data from the outdoor reality and to get the right model parameters. Then we developed four physical models comprising the ride suit, in which each model represents a physical phenomenon. The user can decide which one of them he wants to select, creating his own tire model accounting for the aspect needed for the work. And finally, we develop methodologies, testing devices and procedures, able to get the proper data from the tires, feeding the models thanks to the fast and non-destructive analysis. So let's move on the journey. So in the last years, we focused on the technological transfer of our methodologies from the research to market. We developed our software models in their closed and final shape, creating the ride suit and its modules. Now we are focusing on the procedures and standardization with the aim to offer to our partners well-defined routine that in about 6 weeks can bring from the black and rolling object to the multiphysical digital twin. So the first step involves getting tire data. I will give you further details in the next slides, but the main aspect in our approach is to be compliant with anything else. So you can have force and moment bench, dyno hubs, trailers, or working with vehicle data by means of the tools we can provide. Second step, characterizing tires. So in a multiphysical approach, it means to characterize from thermal, viscoelastic, structural, wear point of view. So it depends on which module our partner wants to work with. Then, third step, implementing these tire parameters inside the physical models of the ride suit. There is the thermal model ThermoRide, the advanced magic formula ADRide, the multi-contact model 3D Ride, and the wear model WearRide. Then, of course, we need to calibrate and validate the models thanks to the data acquired during specific outdoor testing session carried out with sensed tire and vehicles. And finally, we get our target, having a multiphysical replication of the tire behavior that can be used in several application scenarios, from data analysis to software in the loop, driver in the loop, etc. So, once provided a global overview of the presentation, let's go back to the beginning, so getting the tire data. So the first step to meet the tire involves getting dynamic and kinematic data from it. So we all know that there are several different methodologies. Some of us use force and moment bench, some of us use dyno hubs, some of us use the trailers and the outdoor friction testers. We don't have problems with all of them. We get the data from these kind of tools and we subdivide them in dynamic data, kinematic data, temperature data, and wear profile. All this information is analyzed by our tool that is called ADELAB. ADELAB is able to keep all these parameters and to put them inside our physical models. In case our customers don't have this kind of technologies available, so they don't have frozen moment bench or they don't have trailers, they can use, and we usually prefer this kind of solution, the real outdoor data, because outdoor data means real tires, real road, real working conditions. For this kind of users, we developed the trick tool that is able to convert the vehicle sensors data in tire data. It's a physical vehicle model, and it allows us to convert the data from the vehicle to the corners of each corner of it. So in the last couple of years, we also worked a lot on the trick tool because it allows us to work with heavy vehicles. So we have the trick for truck, also with two wheels vehicles. So we have the trick for bike, and we also are working a lot with the new CAN bus and the evolution of the vehicle data we are going to face with, and so we are developing a 2.0 version of the trick. We are also coupling all these methodologies with the real-time onboard state observers that of course are growing up quite a lot in our vehicle dynamics community. Let's go to the second step, so characterizing tires from a multiphysical point of view. The first stage usually is characterizing them from the thermal point of view. So if one of our users wants to work with the thermal model, we can identify the thermal conductivity and the specific heat of each different layer constituting the tires by means of a specific non-destructive and proprietary methodology that allows us by means of thermal cameras and laser beams to identify such quantities. Once the test has been carried out, testing the tires with different levels of thermal power, we can identify the functions with which thermal conductivity, specific heat and density change for each different material and layer of which the tires is constituted. Second step, as concerns the parameterization, means viscoelastic one. We developed in the last, again, couple of years, a new device. It's a patented device. We have a patent in many countries of the world nowadays that is called the VI-grade2021. VI-grade2021 is a non-destructive tire viscoelastic testing device. It's completely portable, fast, and easy to use. It allows to get the data live from track for the development of strategies to get the right compounds of the tires we have in our garage, and to create objective data for physical grip and wear models. It works more or less as a sort of gun, and it can be useful both on brand new tires in order to, for example, get the quality check, so to check that the tire manufacturers is giving us the proper tires, to create a compound characterization database. It's quite useful usually in the motorsport categories in which we have several different compounds, for example, or it can be useful to understand which kind of curing we can create and we can use in order to have the optimal effects. We can use it also on working tires because it's very useful to understand how the viscoelastic properties of the materials are changing during the wear and degradation progressive effects. This kind of tool has become quite famous in the last weeks because quite a lot of F1 teams used it during the Bahrain test, and so here there is a nice press release recalling all the ones talked about our innovative device in the last months. Let's go to the third point. So we can also parameterize in our tire lab the footprints. So we are now equipped with the TechScan bench. We have an hydraulic press that allows us to vary vertical load, inclination angle, and inflation pressure, and it can be used also on motorbike and light truck tires. We are developing proprietary tools for the visualization and the virtualization of these footprints, and they are very useful, of course, to feed the thermal model, the wear model, and the multi-contact model, because of course we need to know in any moment on which area and in which extension we need to spread the energy that is generated at the tire road interaction interface. Finally, we are working a lot on wear models in the last in the last years. And so one of the most important characterization we need to provide is the one related to the road roughness. So we are providing quite a good expertise on understanding roughness indexes behavior, both in terms of correlation with grip and with wear. And so in this moment, we are nowadays able to feed our tools together with all these very important parameters, both on macro roughness and micro roughness road scales. So third phase, once we have all the information about the parameters of the physical model we need to work with, we go to the modularity. So again, we developed a modular multi-physical platform. So we need to put all this information together and to put them inside inside the model, inside the different modules that are able to replicate different aspects. So we have 4 different physical models: thermoride, other ride, 3D ride, wear ride. Thermoride talks about temperatures. Its inputs are the footprint, the thermal parameters, and of course the vehicle entire input data. They are processed inside a real-time analytical model that gives us the tire temperature local distribution, the tire energetic contribution, the inflation pressure, taking into account, of course, of rim temperature, of tread thickness reduction due to wear, and so on. Otheride is a patented model that is an advanced version of the Pacheco magic formula. It works more or less equally to a Pacheco model, so it has more or less the same classical inputs, but new inputs are tread temperature, road roughness, compound viscoelasticity, and much more. Its outputs are more or less the usual outputs of a Pacheco, so it can be inserted in a classical loop with a Pacheco model, but it's able to take into account all the multiphysical aspects concerning with temperature, and again, roughness, compound viscoelasticity variation due to degradation, and so on. The 3D ride model is a multi-contact module, so it's very useful inside the driver in the loop activities because it allows to go over the problems that the usual single point contacts model have. And finally, the wear ride model is the new one. He works with road characterization, as said, with the compound characterization that come from the Vesevo innovative device or from the DMA characterization of the tire makers. It works with the local temperature, pressure, and speed in the footprint. We have a physical model that works with this data and gives the tread thickness reduction and degradation that can be an input for the other models. Now we can go to the testing ground once back, because usually in our activity with our partners, we work organizing and developing some specific outdoor testing session. They are used because, of course, we need to calibrate some specific physical aspects. In particular, for example, the footprint dynamic shape effects or the aero design that act on the air, on the tire convection with the external air. We need to parameterize the strain energy loss component of heat generation and all the correlation between, for example, the wear and the viscoelasticity. So we go back to the testing ground and we can validate some of the models. For example, for what concerns the thermal model, we validate it by means of specific acquisition with the vehicle properly instrumented with infrared sensor at the inner liner and at the external surface temperature with inflation pressure sensor, and we are able to validate and to calibrate a multi-ribbed model. So we are also able to work, for example, with high-performance motorsport bike tires that go up to 65 degrees of camber angle. So it's a multi-rib model that has a high discretization in terms of circumferential, lateral, and radial direction. We can validate, of course, also the dynamic model, so the advanced Pacheco model. It can be validated by means of data that come from the instrumented vehicles, or from, of course, the data from the test benches, or in general from the global fitting of the global behavior that the whole vehicle has, if compared with the simulated model with the tires that has been implemented by means of Otheride. We can, of course, take into account, thanks to this model, of the correlation between the grip and the temperature with different level of thickness at which we measure our virtual temperature, or we can take into account all the cornering stiffness and braking stiffness effects when the temperatures vary. So in this way, we are able to calibrate the global overall vehicle behavior in terms of vehicle dynamics. We can, of course, validate and calibrate the wear model because we just need to get some data about the progressive thickness reduction of the tread on the proving ground, and we can calibrate and validate it with what happens inside the compound, because the compound changes dramatically its behavior in terms of viscoelasticity at increasing mileage, and so in this way we can understand how we can set the proper values at which the tread is going to reduce the thickness, but moreover how the performance is changing because the degradation effects are coming out because the compound is changing the global behavior. Finally, we validate our 3D ride model. It's a sort of ride model in which we have a multi-contact envelope of the asperities. So when we hit the curb, when we take the macro texture of the 3D scenario on which our simulation is running, we can understand which one is the real vector at which the force go to the suspension system and what's the virtual plane in which the force exactly acts at the center of the footprint. So now we have all the ingredients of the receipt. So we have the final tire digital twin. So we can understand which ones are the potential scenarios of use. So we developed the ride suit with a specific aim to be totally compliant to any kind of tire interaction model and simulation environment. And moreover, it's totally real-time in any kind of application, and we don't need to rebuild or recompile or change something inside the model. It's always exactly the same model that is useful for data analysis application, performance optimization application, or in driving in the loop application. It was born to be real-time, it will be real-time in any kind of application. So first kind of scenario, it can be used in standalone applications. So we get the data from flat track, from outdoor vehicle data, from vehicle simulation output. We analyze all this data with all the physical models in order to understand how, for example, to optimize the warm-up phase, to understand which ones are the heat exchanges or the thermodynamics analysis to optimize the thermal behavior and consequently, of course, the performance and adherence behavior of the tires. We can perform some specific analysis in terms of dependencies, for example, of the grip on in the temperature, on wear and degradation, and of course on road roughness and tread viscoelasticity. Second scenario, for example, can be for the offline simulation. For example, in last year, in 2020, we worked with VI-grade with a very nice case study that was involving the Mercedes DAS system. It's the classical software in the loop simulation environment. So we have our desktop vehicle simulation that can be Realtime, ADAMS, or your own model in MATLAB. You have, of course, the ride suit model that gives you all the quantities that are in the loop, and it can work for car, for bike, for truck, and it can be, of course, taken into account also to read the road profiles in terms of interacting with the external virtual environment. Third kind of scenario is in lap time optimization. So we made a very deep work with VI-grade together to work with the max performance tool. So today we are able to take into account of how the performance of the tires is changing in terms of wear, in terms of grip variations, in terms of coronary stiffness and braking stiffness variations due to temperature, and to take in account all of this inside the lap time optimization tool. The logic is more or less the same of the software in the loop logic, but here we have an optimization logic that allows us, for example, to make some specific setup optimizations before, for example, of the race weekend or before to put in production a specific vehicles. And so we can vary, of course, the inflation pressure, the blanket temperature, the ride height, the vehicle balance, and so on. Then, of course, we have the real digital twin in the real-time platform. So we have the real-time scenario in which we can drive our ride suit model. It's a physical model. Again, it is already optimized for real-time. So we have 4 tires working in parallel. We have enhanced the feeling, and in particular for subjective analysis, it's very important also to have the multi-contact 3D ride model. And we also have some more modules that can be used by users of driving simulators at different levels, because we have luxury and racing car manufacturers that equipped our models. There is some motorsport teams working in different motorsport challenges, and there is also some passenger GT vehicle manufacturers. So in this moment, our models are able to go towards a very wide scenario of users. Where are we going now? We have some technical targets quite close. In 2021, we will release our ride to 2021 in June. Inside it, there will be also the ride tool. It will be featured inside. What's the ride tool? It's a tool that allows to the customer to become more and more independent from us. So they will be able to customize and calibrate the model using their own data without every time passing through us. And our tool to do this job, called AdaLab, is ready for the market. It's a tool that allows to the user to get the data from the experimental platform that allow them to get information and to process them from the multiphysical point of view, getting all the data that have been put inside the different physical models. We are growing up, as I told you, and we have some strategic targets. We are opening very interesting new markets, because we are now extending our activities towards North America and Japan. We are also going to hire new resources in terms of PhDs and full-time people inside MegaRide. And we are going to open a new business branch that will be focused on tire-centered control for real-time application, for onboard application, and for what concerns the new frontiers of the autonomous driving and where the autonomous market is going. Okay, I think this is all. This is my contacts. You can of course contact us in any moment for questions, for any kind of further information we can provide, and to follow us on the social media. That's all, and thank you so much for the attention.